So welcome to the seminar from our institute, the IAPS Institute. I'm very nice today to introduce Professor Hyatt that is visiting us. I will leave the introduction to Juan, but before giving the floor to him, I will ask people that have questions for the seminar to keep them until the end of the seminar and not interrupt the speaker in the floor. So Juan, please, if you can introduce us.
Thanks. So it is my great pleasure to introduce Professor Mark Hyatt from the University of Massachusetts in Amherst. That is one of the most prestigious public schools in the United States. Mark has devoted his career to the cold, neutral interstellar medium. And in particular, many of the things that we know about molecular clouds come from the work of Mark. CO was discovered in the 1970s. The beginning of the 80s, we discovered that it's distributed in clouds. And most of what we know about what is happening in those clouds, how they look, their morphology, and how they move their kinematics, comes from Mark's work. So we know him from his excellent review of molecular clouds in 2015, next to Tom Dane. We know of his analysis of principal components in the kinematics of molecular clouds. And when I started in this business, I was introduced to the higher relation that relates the velocity dispersion, the surface density, and the size of molecular clouds. Mark acted as associate director of the 5 College Radio Astronomical Observatory for 13 years. So this was the machine that really built our modern concept of molecular clouds. Mark has been working lately, well, besides, for example, comparing magnetic fields and the structure of molecular clouds, on how the molecular clouds are formed out of the multi-atomic matrix. So, Mark, it's a great pleasure to have you around, and the floor is yours.
All right, thank you, Juan, for that introduction. Thank you, Eugenio, for hosting me this week, and thank everybody for making my stay very enjoyable. I'm feeling very productive working with Eugenio this week. Today, I'm going to talk about some research I've been doing on converging flows in molecular clouds using SOFIA. But I first want to acknowledge my collaborators on this project. The first, Paul Goldsmith at JPL, Robert Simon at the University of Cologne, Rebecca Aladro, and Oliver Rickens, both at the Max Planck Institute for Radio Astronomy. Oops. So we astronomers have been, treated for the last 20 years with spectacular mid-infrared imagery of localized star-forming regions in the Milky Way and in nearby galaxies. It started with Spitzer in 2003, the launch of Herschel in 2009, and more recently with JWST. It gives it that mid-infrared view of molecular clouds, allow us to stare into the clouds and identify young stellar objects in the earliest stages of their evolution, all the way from class 0, class 1, class 2, into class 3, and perhaps all the way to the main sequence. We'll have a much better understanding of that process thanks to James Webb over the coming years. But there's one really key bottleneck in our understanding of star formation. That is, where do those molecular clouds form? How do they form? And how they form, does that impact the product of stars that ultimately form within the domain? So that's the theme that I'm going to be addressing today, in particular on converging flows. I'm going to first review the various mechanisms that people have proposed for formation of molecular clouds. I'm going to talk about 2 theoretical works with simulations that justify or motivate the observations we propose to use SOFIA for. And then finally, I'm going to present those observations from SOFIA in our analysis that all related to flows of atomic gas onto molecular clouds. Okay, well, we've known for over 50 years, we know about the microscopic processes of forming molecules. That is, molecular hydrogen forms on dust grains. Once they form, they're ejected off the dust grains and into the gas phase. Right? molecular hydrogen is destroyed by far ultraviolet radiation, which is absorbed by the molecular hydrogen line, gets excited up into the Werner or Lyman bands, and then 15% of the time when they de-excite, they go down into an unbound high vibrational state, which destroys the molecule and returns those two atomic hydrogen atoms to the atomic gas phase. Because of that FUV radiation, you require a self-shielding layer to protect the molecular hydrogen forms inside that. So you need a self-shielding layer. Carbon monoxide, or CO, our primary spectral line tracer, is also formed in the gas phase, but it also is destroyed by far ultraviolet radiation. So it too requires a self-shielding layer to build up abundances of CO enough to allow us to detect it, then relate that its connection to molecular hydrogen. You can see from this diagram that because of those two self-shielding limits for molecular hydrogen and CO are different. There's a regime in molecular clouds where you can have molecular hydrogen, but the abundance of CO is very, very low, undetectably. So you wouldn't be able to detect the CO. And that's the so-called dark CO gas component. I'm not going to talk too much about that today, but just want to emphasize that it's there. I believe that there's CO dark gas out there. That's just not going to be relevant to what I'm going to be talking about today. All right, so those are the microscopic processes of molecular hydrogen formation. But you need macroscopic processes, all right, to develop those self-shielding layers that allow molecular hydrogen CO to form and to build up their abundances. All right, well, this has been a debate going back all the way to the 1970s of beginnings of millimeter astronomy, of whether you have sort of a top-down cloud assembly process or a bottom-up assembly. In the top-down process, molecular hydrogen emerges from dense regions formed because of instabilities that are triggered by shocks from spiral density waves, supernova remnants, or converging forms. Those clouds get disassembled either by the feedback from newborn stars or when they exit the spiral arm. The shear in the inner arm regions will tear those clouds apart, and exposing those layers of molecular gas will return to the FUV, will return the hydrogen back into the atomic gas phase. So when we talk about cloud lifetimes, that is usually equal to what I call molecular lifetimes, how long a molecule is evolved. And that's going to be limited to about an arm crossing time in spiral galaxies, so it's about 10 to 50 megayears. Okay. The bottom-up cloud assembly method is that GMCs build up from existing molecular hydrogen clouds in spiral arms. And those GMCs get disassembled into smaller but still molecular clouds as they exit the spiral potential and transit into the next arm. So in this case, they survive that transit from one arm to the next arm, and then they repeat that process again. So the schematic here, shows what's that happening. That sort of blue area. Now you can have both processes operating at the same time in a galaxy. In the inner galaxy, the time between spiral arm interactions is fairly small, right? So the cloud can be build up into a GMC, a very large cloud. When it disassembles into smaller clouds, they're still molecular, but they can survive the transit time to the next spiral arm. Where that process gets repeated again, you build up into GMCs, go through the spiral arm, disassemble back into molecular cloud fragments in the inner arm region. In the outer galaxy, it takes a long time to have a spiral arm interaction. You're outside of co-rotation, so in this case, the spiral arms are catching up to the molecular clouds, but it still takes a long time, hundreds of millions of years. So those clouds are not going to survive the harsh environment of the inner region. They're going to be exposed to ultraviolet radiation. Over 100 million years, they're likely going to be returned back into the atomic gas phase. So those are the, again, proposed mechanisms for, in a very general sense, of molecular clouds. I'm going to discuss converging flows. The first paper I'm going to talk about is a simulation paper where they simulate two colliding atomic clouds They follow the chemistry of hydrogen and carbon in a simplified network. The total mass is 40,000 solar masses, so each cloud is 20,000 solar masses. They have two flow velocities, this total velocity of 6.8, that's a slow flow, and 13.6 kilometers per second is the fast flow. Once the simulation is halted, once the sync particles appear, because I don't want to get into the mess of feedback mechanisms that affect star formation, they affect cloud structure. They just want to know how long does it take to form a cloud. Initial conditions they start with is 1 per cubic centimeter, density 5,000 Kelvin. All right, that is in the unstable part of the regime in the thermal stability. So you're starting off with unstable gas. Now it's not warm, it's not cold, it's just unstable. Okay, so I have a simulation that Paul sent. These are the two clouds. This is just an idea of what the process is. These two clouds are coming together. I'm not sure if this is the fast flow or the short, slow flow. All right, but you're going to see that the envelope is going to start interacting with shocks. As they come merging together, you get more interactions between the two clouds. You have flows colliding into each other. That's going to form higher density regions. It's going to transition all that unstable gas at the beginning, initial conditions, into cold neutral gas, and in some cases warm neutral gas. You're also going to form filaments that we connect with molecular cloud structures. So that's the idea of a converging photon. You're driving two things together. You're going to have instabilities develop that'll form density concentrations that allows the formation or moving gas into the hydrogen into the cold neutral mode, and from the cold neutral mode, you're going to have molecules. Let's look at that a little bit more carefully in some plots. What I'm showing here is the cumulative mass of each different phase as a function of time. I apologize for those who have color blindness, but so the orange line that you see here that corresponds to gas between 350 and 8,500 Kelvin. That's how you start off with. That's the unstable gas. You can see very quickly by 3 megayears, you're building up the abundance of cold neutral gas in that blue line. That quickly rises. And then as the simulation proceeds up to about 6 megayears, you start forming molecules. Because you have higher density regions, cold molecules are great coolant, so you can begin cooling down the temperature to, in this case, lower than 30 Kelvin gas. And then ultimately, you get out to 16 megayears. You can see that very little in the slow mode, slow flow, corresponds, gets put into the warm. Yeah, so then by 16 megayears, they stop the simulation because that's when the symptoms appear. All right, in the fast flow, you have the same process going on, but everything is happening much faster. See here, the timeline is from 0 to 16 megayears. Here it's from 0 to 6 megayears. So again, you have the unstable gas quickly transitioning into the cold neutral component, the blue line. You have formation of molecules happening by 1.5 megayears and quickly rises. And you have more, because of the fast flow, you have more energy. You have more gas going also into the warm. So it's very similar, but everything just happening on a faster time scale. More importantly, for what I'm going to talk about, is that what's the abundance of molecular hydrogen and that of CO. So the slow flow, you can see that molecular hydrogen rises up to its asymptotic level really fast. So by 4 megayears, it's basically its limit, and it just stays there for the rest of the simulation. CO doesn't begin appearing until about 5 or 6 megayears into the simulation, but it actually stays very, very low until by 14 megayears. There's a fast rise of CO abundances, and our typical abundance that we observe, molecular carbon monoxide, is 10 to the minus 4. You only get that at the very end of the simulation, just before the sync particles appear. Right. So for a long time, this is all dark CO gas. You have lots of molecular hydrogen, very little CO that you could detect. It's there, but it's at such a low abundance that it would be total. Right. And the fast flow, again, everything is the same, but it's just happening at a much faster scale. It rise very quickly with the molecular hydrogen abundance. There's a little bit of delay of CO formation, but it's very low to begin with, and then rises to its nominal abundance by 4 megayears. And the simulation stops. Okay, so that's the basic underlying idea of converging flows and forming molecules. Instabilities that pushes gas into the CNN. The CNN is where molecules also form. That's great for understanding sort of the physics of converging flows, but as an observer, can we actually measure this? So the second paper that Paul wrote with his collaborators was, taking these simulations and doing the forward modeling of the simulations into the fine structure line of ionized carbon, the fine structure lines of atomic carbon, and then also CO. I'm going to be using C2. I say C2, I'm implying that is the fine structure line. If I say C+, that is basically ionized carbon. There's a distinction between the two. Right? I may kind of use those interchangeably, which I shouldn't do. All right, in this simulation, they're just doing a slow flow. They vary the interstellar radiation field and the cosmic ray ionization rate, just to see the impact of that. Again, the simulation is halted once the sync particles appear. And then they do the forward modeling to generate line profiles and intensities of the C2 line, 2 carbon fine structural lines, atomic fine structural lines, and CO. So now that's been putting us on this observational domain that I feel more comfortable as an observer. I'm going to skip many of the details. I'm going to go right to what I think are the kinematic signatures for converging flows, and that's sort of what the point of their paper is. But first, a few comments. Most of the C2 emission that they see in their simulation, and then this is at the time frame at the very end of that simulation. So you formed a lot of CO gas, molecular gas, just before the sync particles appear. So most of the C2 emission at that point is coming from atomic gas. There's not that much dark CO in their simulations at this stage. The brightest C2 emission is aligned with the atomic carbon fine structural lines and the CO. That is this bright. So the top upper left hand is the position velocity diagram of C2. Upper right is the atomic 1 to 0 atomic fine structural line. The 2 to 1 fine structural line is the bottom left, and the CO is the bottom right. So you can see that the brightest C2 emission is aligned where you see most of the C1 and the CO emission. All right, but they point out, do you have a pointer? That's all right. So they point out, looking at the C2 position velocity diagram, that there are these 2 features at plus 4 kilometers per second, minus 4 kilometers. We're at the edge of those points. They associate that emission with the 2 colliding clouds, CNN within the 2 colliding clouds. All right, but you see these striation features that connect those features at plus and minus 4 kilometers per second. They connect that to essentially the bright emission at 0 kilometers per second. And that, they propose, is the material that's accreting onto the higher density regions that are ultimately forming the clouds. You don't see those striation features in the C1 or the CO because that's where the material is falling onto. Right? But I would say, in their paper, they said this is going to be really hard to detect. The antenna, or the brightness temperatures of this CNN gas that's in these striations is less than 0.1 Kelvin. So you have to integrate down to 0.03 Kelvin just to get a 3 sigma detection.
Is there magnetic field in these simulations?
Sorry?
Is there magnetic field in these simulations?
I don't think so. Yeah, definitely not. Okay. Anyhow, so that's our signature for looking for accreting flows or converging flows onto molecular clouds. And they said, this would be really hard to detect, but they suggested, find a compact molecular cloud and start sampling around that molecular cloud to look for these striation features that are offset from the main velocity of the cloud. So we took that information and we wrote our proposal to Sophia using the upgrade instrument that is focal plane array with 14 pixels, with frequency that includes the C2 line, with great spectrometers, 14 arc-second beam at the frequency of the C2 line. Now, we proposed several objects to observe. We only got time to look at one object, and that was in the outer galaxy, which is fine, so we had to be very careful about selecting what object to look at. We wanted to find an object that was very isolated so that we can bring in the 21 centimeter line mission to sort of add that to our analyses of what's going on in this region. So this is our cloud at BKP 7323, which is from a catalog of clouds in the F-Stereo outer galaxy survey that we did in the 90s. The cloud you're looking at is that bright feature toward the middle of the figure. You can see that there's nothing. This is integrated over the velocity interval of that feature. There's really nothing very close to this cloud. So it's very isolated, not just spatially, but also kinematically. So hopefully that allows us to bring in more information from the H1 21 centimeter line. All right, to give you a little bit more information, if I zoom in on that so you can really see what it looks like, well, the 14-meter telescope is 45 arc-second resolution. Yeah, you're sort of resolving the cloud, but it's not really well resolved. That's okay. The distance here is 3.2 kiloparsecs. I think that's from Gaia. Total mass, molecular mass, is 1,100 solar masses and 3 parsec radius. There is star formation activity going on there. We sort of wanted that to make sure that, if we didn't see any CNN, we may at least do some PDR science as sort of a backup. So in the end, we have data from SOFIA, the C+ line. We have our CO data from the Galaxy survey. It's not great sensitivity, but sufficient for what we want to do. And then we have H1 21 centimeter line data from the Dominion Radio Astrophysical Observatory Canadian Galactic Plane survey. Okay, so the background image is again a CO map. Well, we didn't have a lot of time, so we wanted to be as concise as possible. So we decided just to do a cross map along the longitude and latitude axes. So this is the after regridding, this is the sample of C+ points that we have lying on top of the CO integrated intensity. Right? So it'd be nice to go out a little bit further, but again, given the limited amount of time, we are very conservative. And this is the C2 image integrated over the velocity interval that we expect. Now, you see that really bright feature, which is offset from the center of the cloud. I was thinking, oh my God, I gave them the wrong positions. I was expecting, the C2 to be bright where the CO was, but it's offset. And that a bit of a mistake on my part, but I'll show in a few minutes that wasn't a mistake. That's legitimate. The point to note here is that I've set the scale here at 3 sigma at the bottom level. So any point of black is less than 3 sigma, but almost all the points have a detected C2 line. So in some sense, we were kind of pleasantly surprised how on the extent of the C2 emission that we observed. All right, so to putting all the data together, what I'm showing here is on the left, on the first column, are integrated intensity maps of C2 line, of the CO. Contours are 850 micron map from SCUBA. And then the H1 21 centimeter line, all based on that one box defined by C2. And the middle column is the longitude velocity diagrams, and the right column is the latitude velocity. Okay. So what you can see from here is that the C2 emission is lined up with the same velocity as the CO, both in the galactic longitude maps and latitude maps. However, if you look at the H1 has a peak, sort of on close to the top of the cloud, but the position velocity maps show H1 emission is offset from the C2 and the CO gas, both in latitude and longitude. So if we look at the 21 centimeter map a little bit in a little larger field of view, the white rectangle here is essentially the size of the C2 map that I was showing before. You can see there is a fair amount of extended H1 21 centimeter line emission over the somewhat larger velocity interval than you see from the C2 CO. You can see that there's a hole there on the right-hand side. That's a background extragalactic source and continuum. H1 will absorb that continuum, and so you see the gray spectrum there from that position, the absorption feature of that background continuum source. That is the signature for presence of cold neutral gas in the vicinity of this molecular cloud. The other spectrum I showed was just a point offset from that, just to show that the absorption is limited to the position of the extragalactic source. Okay, so we know that there's C and M gas in the approximate vicinity of this molecular cloud. It'd be great if I had a continuum source right on the cloud, but we don't have that. Okay. So I said that there was star formation going on inside this cloud. The top left corner there is the C plus map again, C2 map. The other ones are 24 microns, 70 microns, 160, 250, and 850. So now you can see why the C2 line is so bright, offset from the center of the cloud. There's actually a fair amount of star formation going on in that position, as well as that there's lots of star formation going on. Probably about 10 sources that are identified in the center of the CO cloud. So what you're seeing here, and what you're seeing throughout the map, it's not C and M gas again. This is mostly bright PDR emission, right? That's being illuminated, so the young stellar objects are illuminating the surfaces of the cloud, of the gas, and creating essentially PDR emission, which C2 is very sensitive. So that's the reason why that bright feature is offset. Okay, well, we didn't want to do PDR science. It was sort of the last hope. But so just to very quickly, we use the PDR toolbox by Mark Pound and Mark Wolfire, which they calculate the C2 intensities as a function of volume density and radiation field. The red lines that I show in the top left box, this is for the C2, is the R3 sigma point, which is the lower line, and our peak isotope. So, just one line doesn't constrain the density or the radiation field very much. I can add a CO, which is the top right box. Again, the one line to the left is the 3 sigma point of our observations, and the right line is our peak isotope. And then just for redundancy, I can also look at the ratio of these two. You put all those lines together and you find where they intersect. That's filled in by this gray area. And so it tells us we can put constraints on the volume density to be a few hundred, 10 to the fourth. That's not too surprising. In fact, knowing what I know about molecular clouds, I think I would sort of believe it's more on the 100 to 1,000 range more than up to 10 to the fourth. And the radiation fields, are going to vary between 1 and 10. We don't have a great measure. We only have 2 lines, so we really can't constrain those values much more than saying that we're between 1 and 10 and G0. And again, none of these embedded stars are massive stars that are dumping a lot of UV radiation, but they're probably A and B stars that are certainly enough to illuminate surfaces and generate a dense PDR action. And that's all I'm going to say about PDRs, hopefully for the rest of the talk. I want to get back to converging flows, because that was really our main emphasis. So here's our map again. And we knew from the very beginning when we wrote the proposal that we were going to have to do a lot of averaging of the data that we did collect. We repeated this cross map many, many times. That got us down to an RMS about 0.2 Kelvin. Remember, we're looking for detections of 0.1 Kelvin less. Yeah, so we were going to average up some data, so that's what I'm going to show now. These are positioned along the horizontal cut, the vertical cut, and now I've increased the saturation of the images a lot more from what I showed previously. The saturated points that you see at minus 40 kilometers per second is that PDR gas. But you can also see there's a sort of a very faint level of emission between minus 43 kilometers per second and up to minus 50 kilometers per second in both the horizontal and vertical cut. I could do a little bit more averaging to actually show you the spectra, and so you can actually believe me that between minus 50 and minus 43 kilometers per second, there's a blue shifted wing of C2 emission. That's clearly offset from the PDR, the strong PDR, which is at about -40, -41 kilometers. All right. So that's what I'm going to focus on for the rest of the talk. Okay. Again, we're going to do a little bit of averaging. We want to get some more spatial information. So we have, we average up spectra along the horizontal cut, vertical cut, different locations. And you can see that we filled in sort of where we see the blue shifted wing with gray. You can see that we see that blue shifted wing throughout the map. So this is a very extended component. It's not limited to one part of the map that we've made. And again, just to remind you, looking at the top, the H1 21 centimeter plot on the right that I showed earlier, there's the absorption of the continuum is happening between -50 and -41 kilometers per second. Right? So the same regime that we're seeing in this blue shifted emission, blue shifted C2 emission. Now it's very important to understand, is there any CO gas associated with that? So, again, the sensitivity of the CO observation wasn't great because it was part of the big survey. All right, but I averaged up all the CO spectra in the range of the C2 map. And if you look at this blue shaded area here where we see the blue shifted feature in C2, you don't see any evidence for any CO emission. All right, so that could be one, that dark CO component, that you have lots of H2 there and not CO because the abundances are low, or there's simply just no CO gas there. Well, just leave it at that. And there may not be any hydrogen gas either. Anyhow, so we have two components. We're going to try to separate those components. I'm going to do a Bayesian fit, to get two components out of that. The red lines are the PDR component. Blue lines correspond to the blue shifted component. So I want to be able to separate those out so I can do some calculations with those. The first calculation is looking at volume density. From two papers by Bill Langer and another one by Paula Goldsmith, that worked out the column density, the relationship between column density and C2 emission. And Paul looked at the collisional excitation of the C2 line. You can derive an expression for the volume density under the assumption that everything is optical. Okay? Collisional excitation of the C2 is only with hydrogen, and here I've had set the temperature, kinetic temperature, to 100 Kelvin. So, but you see that there's an X in here, in the denominator. That X is simply the ratio of the column density of C plus divided by the integrated intensity of the C2 emission. The column density of C plus, we essentially integrate the hydrogen 21 centimeter line and then just apply a ratio, the abundance ratio of carbon to hydrogen to get a C plus column density. And the C2 integrated intensity comes from our Gaussian fits, assuming the definite integral of our Gaussian. But now I propagated all the posterior distribution of the Gaussian parameters through here to get my error bars. So the plot here, I'm showing essentially the volume density as a function of offset. And you can see that there's no central concentration of this blue shifted component, whatever gas is responsible for blue shifted. All right, but the average here is about 70 particles per cubic centimeter. That's sort of what you associate with cold, neutral, medium gas. So one can ask the question, what is the blue shifted component of C2 emission? Well, the C2 intensities are comparable to the predicted values of CNN gas in simulations, about 0.1 Kelvin, more or less. The C2 signal spans the same velocity interval as that absorption feature toward the background continuum source. That we know is a signature of cold neutral gas. And the derived volume densities that we measure are sort of what you expect for the cold neutral gas component. So that blue shifted feature, I think, is clearly cold neutral gas, hydrogen. Possibly dark CO gas. Okay. All right, so that I think we've established that fairly readily. But now the real question is, what is the relationship of that feature to the CO cloud? And this is where it's going to get kind of ambiguous here, because I don't have all the information I need. All right, but I'm going to go through all the options. First, I'm going to tell you what it's not. And it's what the emission that we see can't be due to an atomic envelope of the CO cloud, even though it's sort of everywhere in our map. All right, but our CO mass is 1,100 solar masses. Our radius is 3 parsecs. I can calculate a variable velocity, right? See if that's, what velocity range, you have the velocity differences. We keep that material bound to the cloud. And you can see it's only 0.6 kilometers per second. But, our offset of that feature from, the CO cloud is 4 kilometers per second. So 4 kilometers per second, that would simply drift away from the molecular cloud in about a crossing time, which corresponds to about 1.5 million years. So I don't think, what we're seeing in that blue shift component can be related to the envelope of the cloud. Another option. Okay, so this is what the options of what it could be. All right, this could be just, it's 4 kilometers per second displaced. I don't trust kinematic distances in the galaxy that carefully. But 4 kilometers per second in this range of the galaxy, this longitude, corresponds to several hundred parsecs. So, this feature could be just another CNN cloud that's floating in the galaxy, has no connection whatsoever to our target cloud. All right, so it's almost a trivial result that this is just another cloud. Who cares? And I can't argue against that, but it's also not that interesting. So I'm going to say it, but I'm going to ignore it for the rest of the talk. It could be a wind-driven shell of CNN gas from recent star formation. See that there's lots of star formation going on inside the cloud. Try to discount that one by saying, well, there's no, most outflows from young stellar objects are bipolar. We have no evidence for a redshifted counterpart of CNN gas. And since the CO is really the first, layer of gas that an outflow would see, you'd expect to see a CO outflow. Now, our sensitivity of CO is not great, pick up outflows, but we don't see any CO counterpart to a blue shifted wing. We don't see a blue shift, we don't see a red shift. So I'm going to sort of discount this possible explanation for that blue shifted feature. The next possibility, and the one that I think I ultimately favor, is that the H1 CNM layer of gas is streaming onto the cloud with a flow velocity of 4 kilometers per second. So on the right here, I'm showing the H1 21 centimeter line integrated over the velocity interval, just the blue shifted component. The contour there represents the 8 times 10 to the 20 column density isotope, and the black line is the molecular cloud. So there is, again, a localized peak of H1 gas on the cloud, localized, not the only peak. But there's a fair amount of gas in that peak. There's like 3,000 solar masses of atomic gas associated inside that white contour. I have a density that I showed you I've already calculated. We know the flow velocity is 4 kilometers per second. The size is 3 parsecs, so I can calculate a mass flow rate. That comes out to about 3 times 10 to the minus 4. That seems to be a completely reasonable flow rate. And you could regenerate 1,100 solar masses in just 3.4 megayears at that flow rate. So it's certainly, you could form a molecular cloud in sufficient time based on what the measurements that we've made, the assumptions we've made, in the calculation of the flow rate. Okay, but remember we started this talk about converging flows. Converging flows are wonderful because you've got two things that are smacking into each other, and that's going to form a shock, and it's going to form lots of high density gas. So it seems to be very efficient at forming, the CNN and then ultimately the gas. All right, but here are those position velocity diagrams, and everything's to the blue. You look up, at velocities greater than minus 40%. There's nothing. And you look at the spectrum, there's nothing. There's no counterpart of that C2 emission on the redshifted side. Right? If you're going to converging flow, you sort of need that. You don't have that flow. So now you could sort of wave your hands a little bit and say, well, maybe that flow is coming down from the top in the plane of the sky, so it should be at, minus 40 kilometers per second. All right, but that's being overwhelmed by the PDR emission. You're never going to see that component because the PDR emission is so bright compared to, what we'd expect from the ceiling gas. I think that's a little hand waving. But if you do integrate the H1 emission over just that interval, you can see that there's some sort of faint, H1 gas there. I think that's probably the envelope, the atomic envelope of the cloud, but not necessarily a accreting flow on top. And of course, if you integrate over the redshifted side, all you see is just very faint H1 21 centimeter line emission, probably representative of mostly warm neutron gas at some point. Okay, so I warned you that the results are going to be kind of ambiguous. I mean, I think in summary, we see faint C2 emission. When we spatially average spectra, we can, after we spatially average the spectra that tracks CNN gas or CO darkness. I think that's a pretty positive result. Okay. The velocity offset of that faint emission may be a signature. I'm not going to go on a limb and say it's absolutely a signature to a singular flow of CNN material onto the developing molecules. Now, I have a few caveats with that, as you can imagine, for such a somewhat ambiguous result. First of all, our target cloud is only 1,100 solar masses. That's pretty small. It may not be representative of giant molecular clouds, which have masses greater than 10 to the fifth, and they're responsible for most of the star formation. So, again, we chose that cloud because it was compact, spatially isolated. It's going to be, but it's not representative of molecular clouds and galaxies that form stars. But more importantly, this is a really hard problem. One cloud is not going to give you an absolute result. And measuring the C2 line is difficult. You got to either get in an airplane, which no longer is flying. You do balloon missions, which is what this Gusto project is. I guess that's been launched, collecting data. But ultimately, I think you want to do it in space. And there is a NASA program that is on. I'm not sure what state it's in right now, but it would do the C2 line, but not in the high resolution mode. At least that's the current understanding. The other option is the square kilometer array. Now that gives you, so much more sensitivity than what we have now, that you can begin looking at, more continuum sources, and that are more tightly spaced. That you can start looking at the cold neutral gas for absorption toward the back of the continuum source. That may only be 1 or 2 arcminutes apart, then you may be able to put together a better view of the CNN than what we can do today. But again, it's all really hard. Ultimately, you really need lots of samples to do this right, to really make a convincing result that flows are accreting onto. All right, that's my talk. I'd be happy to take any questions.